morning, guys. Can everybody hear me just fine? That should be better, and I suspect you can hear me. Good morning, guys. Can everybody hear me just fine? That should be better, and I suspect you can hear me. So, I have provided the link to check in for today. That link is in Teams. It's also provided in this live chat. You can access that link any way possible. I do want to make sure you understand navigation for Teams at this point and how it's going to look. I've got it set up a little bit better. So this is what Teams looks like for your class. You'll notice there's a general channel. That's where all of the basic announcements go. Some of you found that and gave me some very, very helpful guidelines for how to set up a calendar. Up at the top of the general calendar, up at the top of the general is a calendar. That calendar is one place where you can access the live streams that will be posted. Now, I'm going to show you the other type of calendar that you are going to be getting this afternoon. This assignment announcement, every time I make a assignment like these check-ins or the Q&A grades or the exam grades, it's going to create an announcement. If it's an assignment that I want you to submit online, i.e. you're going to submit it through Teams, it'll go in this assignment announcement area. If it's an assignment that I am creating so that I can input a grade for you, that's going to go in the DNS assignments, i.e. do not submit assignments. Those assignments are there for me to input grades as I grade stuff. You're going to see a whole bunch of that start pinging if you've got if you have Teams set up to let you know when stuff gets added to it. You may want to turn that off for the next few days and then turn it back on, say Sunday. Because what I will spend the rest of this week doing is adding all of the assignments to Teams. And that means you're going to get pinged a lot. So you may not want to deal with that. Interesting videos is where I will put videos that I think you might find interesting or that I might be using for a bonus, as we'll talk about that as well. Question and answers. This is the other place you can place questions. So like if you have a question today and you don't want to ask it on live stream because, well, it's live stream and you just aren't comfortable asking it there, go put it. Yes, the DNS assignments are the ones you're going to submit in person, and then I will grade. But there are also things like we will have quizzes in Brightspace, and those Teams and Brightspace, they don't link, obviously. So I will download the grades from Brightspace, and I will input the grades into Teams. So things like that. So there's very few things you are going to have to submit in Teams, and most of those are going to be things related to bonuses. So there will be very few things in that assignment announcements, and I'm going to show you the better way to get to all of this. Question and answers. This is the channel where you can post your questions. So every week on Sunday, and that includes this week, every week on Sunday, we will I will go through the live streams the chats for live stream and see who asked questions. It's going to be a little bit hard to identify you guys based on your handles, your YouTube handles. So you might want to put your last name before you type a question, just so that I can get a feel for who's asking questions in the live stream. Maybe then I won't have to make so many guesses. But you can also post your questions in this question and answer. And right now it can be on the syllabus and various other things, but that's where they go. And that on Sunday at 10 p.m., I'll put another announcement like this. It'll say week 2 questions, and that's the stopping point. That's the break. So everything in this channel, because it'll look like this, everything in this channel between the 2 breaks is what I count for your question grades. And those are worth 1 point each up to 6 points. So we're going to talk about some of this again. The best place to go and find all of your information is going to be classwork. So you'll see in course information, there's your link to the Lecture 1 video. Here's the course evaluation and grade scale. I've simplified a lot of stuff, so that'll be updated today. These are the general course policies book. You will be given this book also in print. This book is just basic course policies, so supply requirements, electronics, department honors policies, policy on WU, policy on lecture lab, calculator policies, and then it's all of the learning goals for CUNY, for the department. The reason why this is a separate little booklet is a lot of this you're not going to want to read, but we have to supply it. This does not have the grade scale or the calendar in it because this policy booklet's given to every student in all of the 114 classes, because these policies are for all of the 114 students. The most important thing in this booklet for you guys is the other than the basic policies about meetings, is the course learning goals and objectives. And the reason why these course learning goals and objectives are important is the only questions on the final examination for this course, the department final, will come from these learning goals and objectives, and not the ones labeled optional. The optional goals are things that a professor might choose to teach, but they will not be on the final exam. If it's listed not as optional, there is a possibility that you will see a question on it on the final exam, maybe more than one. So these goals are long and they're detailed, and they're that way because these are the goals that determine the final exam questions. So if you're trying to work out what you should study for the final, this is a very, very good booklet to have. There's also a place in this booklet for you to write down when the makeup final exam is and when the final exam is once I announce it. Okay? And again, you will be given a hard copy of this booklet when we meet in person next Monday. You'll see that this lecture is appearing in Module 0 because we're going to be reviewing some nomenclature here very, very soon. And the lecture check-in link is also here, and that's how that'll appear all of the time. So if you need to get to lecture check-in before 8:30, just click on that link and it'll take you to where you need to go. And this is how we will do this. If I can get links to the Brightspace quizzes, I'm going to put them in here too. So everything's going to be linked in here. Reading assignments will be linked in here. Homeworks and which activities you need to do will be linked in here. Everything will be linked right here. So it should hopefully make this easier to do. And I will, on assignments, work to make sure there's a due date so that you can see the due date when you look here. Okay? Now, the other calendar that you guys will be getting this afternoon, I'm going to the 113 because that calendar is in place. It just takes time to typeset these. You will be getting something that says official course calendar. You can print it. It is a PDF. First page of it will have the definition about bonus assignments, homework assignments. I'll talk to you about body doubling work-alongs. Those are obviously optional. And so forth. I have carefully color-coded stuff. And so it looks something like this. So it has this, and it has all of anything that leads to points in the class is in red with a little checkbox so that you can print your calendar and you can check off what you did. So all of that is there. And that's how this will work for you guys too. And this will go up probably around noon today because I've got to finish typesetting it like this and make sure all the colors are the same. So your exam will be also, it'll be on Monday instead of Wednesday. This is 113, but it'll be on our in-person meeting. Now the exams are not going to move. They're going to be fixed in place, and just whatever material we've covered, that's when they'll be there. But you'll also see it gives you what chapters, oops, I forgot to put module 3 there. It gives you what chapters and so on and so forth. So that's the more advanced calendar. I would like some feedback on that calendar because my autistic side likes that calendar a lot. My ADHD side's like, oh my God, there's so much stuff to do. So this may be a calendar that's a little bit too complicated and a little bit scary at first. So give me some feedback on that, okay? But I tried to make it where everything was in one spot so that it would be easy for everybody to use, where it would be a document that you could put in a notebook and check stuff off. Now that leads me to talking about, because these are the same times for you guys, these optional body doubling work-alongs. So if you have ADHD, one of the issues that arises in ADHD is the inability to start something and stay doing something because you don't get the dopamine rise for completing a task. And because of that, it's really hard when a task is tedious or boring or not particularly interesting. It can be really hard to do it. And one of the things that works and can help people with ADHD complete a task is to have somebody else just be there with them while they're doing it. And that's called body doubling. So, on Tuesdays and Thursday nights from 8 to 11 p.m., I'm going to open a live stream, a YouTube live stream. I'm going to put on some music that we can play. It's going to be generic instrumental music. I am sorry, guys, because if I play anything that is not generic, it will be copyright struck. It's YouTube live stream. Have to have copyrights. So I'm going to just put on some generic instrumental music. I'm going to sit here and write the solution sets to homeworks or grade. And I'll invite you guys to join and do your homework that's due when we meet. And that's why it's set on Tuesday and Thursday. Because homeworks are either going to be due in class or they're going to be due where you can drop them off in the mailbox outside my office door. And these are 2 times to set aside where you can get homework. Since I'll be there, you can ask questions. So it also acts as office hours. Um, but you can just join in. I'm going to put a Pomodoro page up in the link so that you can write your own Pomodoro of these are my goals to get done during my body doubling work-alongs. I'll show you my goals and check them off as we go along, and I'll encourage you guys to check off your goals as you go along, because that's the point of body doubling. They are completely optional. You do not have to participate, but if you want to, join in. Then it gives you at least 6 hours of dedicated time to study for this course. So that's being set aside for that. So I just wanted you to know about that. So you'll see those links. And they're optional, obviously, but if you need that type of help, they're being provided. And that will also help me stay on top of the grading that I need to do for you. Okay, so are there any questions about that? You'll also get the evaluation method. It's going to be very, very close to this one. I don't think this is this is not the up-to-date one. So you'll also get a course assessment grade scale. That is basically how the grades are going to be divided for the course, and the grade scale. Now, one of the things we did talk about last time is bonus. So I said that one of the ways to get bonus is from the CHEM Connections workbook, and that is one way. But some of you, I understand money's tight, so some of you may not want to buy the CHEM Connections workbook, or you just may not want to do that. So there are other ways to get bonus. There will be certain videos that I post that you can watch and evaluate. There will be an evaluation sheet. The department has a seminar that happens on Mondays from 11:15 to noon. You're welcome to go to those seminars. If you go to those seminars and fill out a seminar evaluation sheet, that's bonus. The Alchemy Club has certain meetings and things that they do during the semester. I don't know their schedule yet. Those will be attending. Those are also bonus. And those will just be announced in general. When I get an announcement, I'll post it there, let you know that that's a possibility for bonus. I can't guarantee that those other bonuses will be worth up to 100 points. But the way I do bonus is I put a broad variety of bonuses in there, and you can earn points. And once you get to 100 points, that's the cutoff. So the maximum bonus points you will receive credit for is 100. And the guaranteed 100 points is the CHEM Connections, but there are other ways to get 100 points. Well, there are other ways to get bonus points. It may not add up to 100. The CHEM Connections adds up to 100 for sure. The other place where there are a few bonus points are the online quizzes. There are bonus points there, but that doesn't count towards that 100-point limit. The questions asked during Link, there's like 28 additional points available there that's bonus. Again, that doesn't count toward the 100 bonus point limit. So, the work other than the work required for the class that's grade stage. No questions? Well, just to remind all of those of you that have tuned in a little bit late, there is a form that you need to do. That form is available, and you need to check in before 8:30. Now, I'm about to flip over the break We're going to take a 5-minute break. This was our first Pomodoro. After that 5-minute break, then we will move to the first part of the lecture, which will be a review of inorganic nomenclature and a little bit of a review of structure, especially structure related to organic molecules in terms of shapes. And that'll be our second Pomodoro for the day. So I'm going to flip us over to a Pomodoro break. Don't hesitate to ask questions during Pomodoro breaks if you wish to on the live chat. So the form is located, the easiest way to get to it is to go to Teams classwork, or you can slide up in the live chat and you'll see a forms.office CSH. You'll see a link right up at the top of live chat. You can just click that link. Is located, the easiest way to get to it is to go to Teams classwork. I really need to turn it on. So did that answer your question? So, in terms of the workbook, the first, I know it always takes time to arrive. And um, the first activity, so the first week's activities, which will be due next Friday, those activities I will provide. I will provide PDFs for those activities and for the bonus. Then after that, you'll be responsible and you'll have to let me know. Now, if in the second week of the class you still don't have the workbook, you need to let me know that where I can provide the activity. After the second week, I will not provide it. So, if you ordered from Amazon, if you ordered from Kindle, they should be able to get it to you within 2 weeks. If there's an issue with that, I might go with third week, but after that, I'm not going to do more than 3 weeks. That's 3 weeks into the semester. 4 weeks if you count this week. So, just generally speaking, I will provide activities for the first week. If you ask, I will provide them for the second week. After the second week, you've got to have a really valid reason. I am aware of paydays, so generally speaking, people get paid on the, and I'm aware of living paycheck to paycheck, so generally speaking, people get paid on the 15th or every 2 weeks. If you're on a 2-week schedule, you'll probably get paid either this week or next week, which would make buying a book possible. If you get paid on the 15th and the 30th, you should get paid this week. So that would allow you to order it, and it takes at least a week to get here. So that's why 2 weeks. Okie dokie. But, don't hesitate to ask if there is a problem, because I do understand shipping problems, snow problems, ice problems, a whole bunch of other problems. So if there is an issue, don't hesitate to talk to me about that issue. That's why we have Teams for private chat. So there are 2 workbooks. So I will reiterate this one more time. There are 2 workbooks. The POGL workbook, which is called, this is in the live chat from last time too. Required workbook is called Chemistry, a Guided Inquiry, Part 2. The bonus workbook is CHEM Connections. You can find both of those on the Queens College bookstore. Okay, February 19th through the 26th. Thank you. Send that to me in chat, because if other people bought it on the Amazon bookstore, they'll have the same delivery date. So please send that to me on the chat, where I can remember to provide workbook pages up until that time. Okay? Now, let's talk about inorganic nomenclature. That's a little thick. There we go. Oh, much better. Okay. See, if I know you bought it and you show me your Amazon receipt that says it's due by that time, then technically I'm not violating copyright to provide you copies of the pages to tide you over. I'm violating copyright when I provide pages to somebody who hasn't bought the book. And that's why I need to know stuff like that. Okay, so inorganic nomenclature. The first thing you need to remember about inorganic nomenclature is, if you look over here, if you look at the periodic table, And I kind of put one off to the side. I suspect it's a little blurry, but you don't really need to see the letters more than you need to see the orientation of the periodic table. And at this stage in 114, you need to be very familiar with how this table is set up. And have some idea of where things are. Oops. Well. Okay, so this column is the noble gases. They don't tend to react unless you're down here at xenon. Xenon actually will form molecules. It's really the only noble gas that will form covalent molecules. And that's because it's really, really big. Has a lot of electrons, so it doesn't mind sharing the electrons in the valence layer, the outer layer. This entire region is the P block. This region, which I've kind of drawn truncated, is the D block. And these are the transition metals. And this is the S block. Now, things in the S and the D block, these tend to make ionic compounds. Things in the and also tend to be cations in ionic compounds. Things in the P block can make ionic compounds or covalent molecules and depending upon where you're at in this P block, the ionic nature can be either as an anion or a cation. So generally speaking, if you're up here, it's going to be an anion. And if you're in this region, it will be a cation. If it's in a ionic compound. And this region, kind of right here, is generally speaking going to be covalent bonds only. So the basic structure of the periodic table can help you with that. Notice I didn't even bother with the F block. That's that row, the two 14 sets of 14 elements down that's pulled out of the periodic table to make it where you can actually print it on a page and still read everything. The F block, they are metals. They're very rare. Some of them are used in our electronics, so you can't say that not all of them are useful. Some of them are very useful, but they're extremely rare. Their chemistry is very unique, and generally speaking, if you're going to study and work with F block metals, you're either going to be in solid state physics or material science. And you're going to take specialized courses in those areas, and that's when you'll play with the F block metals. As a chemist, just a standard bench chemist, you're usually not ever going to handle one. You may not even ever see one in your lifetime. So that's why, generally speaking, as chemists, we just ignore those. You can't ignore them in terms of the electron configurations, but for any of the things we're interested in as chemists, these electrons are core electrons, so they don't participate in bonding. So for the most part, we just ignore the F block. Now, we went through all of that so that we can talk about naming. The first thing you have to do when you're making a decision about naming is decide if it's an ionic compound or covalent molecule. So you have to make that decision. And that's why the first thing I went over is what form, where are the ionic compounds, and then where's that little area of covalent. So generally speaking, if your central, your atom of lowest electronegativity, so you're otherwise known in Lewis structures as your central atom, is boron, carbon, nitrogen, silicon, phosphorus, then you're in the covalent compound. You're kind of guaranteed it's covalent. The other ones in the P block, you have to kind of know based on bonding and structure and behavior, if the bond is covalent or ionic. And that means that the bond, the interaction between the central atom and the outer atoms of the compound will have more ionic character. May still be covalent, but it's going to have more of an ionic character. And what that really means is at this stage in chemistry 114, if you really want to be able to go from general chemistry 1 through 114 to organic and have a really strong foundation for organic chemistry, you need to truly begin to think of these compounds, these molecules, these things that we draw on paper as three-dimensional objects. And so the way I suggest you begin to view these things is as little fuzzy pom-poms. I know that's silly. It works. So you have a little fuzzy pom-pom. That fuzziness is the electron cloud. As you move down the periodic table and towards the right on the periodic table, the pom-pom gets bigger because you have more electrons. Bigger pom-pom means you have more places to interact to form bonds. Smaller pom-pom means you have less electrons, and so you wish to hold on to those. Sorry. So generally speaking, your molecule has shape and size. And that shape and size and where the electrons are at determines how the molecule reacts. And that's really, really important in organic chemistry. So if you really want to be good at organic chemistry, you need to begin to try to teach yourself to visualize this stuff in 3 dimensions. And you should visualize the electrons as a density, as a movable density. And electronegativity tells you where the density is the highest. The higher the electronegativity, the more electrons get pulled towards that atom. So the higher the electron density. So if I have an atom bonded to another atom, and the other atom has a really high electronegativity, it's going to pull electrons away from the other atoms attached to it. And all reactions, every single reaction that happens in chemistry, is areas of high electron density reacting with areas of low electron density. And if you can really begin to think about that in that way, it will really help guide your understanding of organic chemistry reactions when you get to that point. So this is a stage in your career, in your life, to really begin to think about this stuff that we write on the page as just a placeholder for a three-dimensional object. And that's why I take the time in the first lecture to go over nomenclature. I go over nomenclature because if you're going to purchase chemicals, you have to know the name. But also because when I assign homework problems, I don't give you the formula for the most part, unless it's something you're not going to know. So nomenclature, and then also we're going to go on to something new for you guys, which is organic nomenclature, toward the later part of this. So you have to decide ionic, covalent. They have different names based on ionic or covalent. Now, on ionic compounds, I'm going to use blue. You name cation, and this is just the element name. And then you name the anion, which you're usually going to replace with an IDE. So, for instance, sodium plus chlorine minus. The element name for Na is sodium. The element name for this is chlorine. Now, at this stage in terms of memorization on the periodic table, you should have all of the names memorized for the first 3 rows of elements. Well, actually the first 4 rows. And there are going to be select things you should have memorized in row 5 and 6. Basically the halogen, basically the noble gases, the halogens, the oxygen row, and kind of the stuff in yellow you should have memorized. In the transition metal area, there's certain things that you need to memorize and certain things that you don't. It'll be obvious with that when you get your data book, which will get uploaded today. So, but if you haven't memorized the first 4 rows, you need to do that. Go create your what's the name of that flashcard site? Can anybody supply that to me real quick? The site that you guys use to make flashcards that will test you. I had a student that used it all the time for anatomy and physiology. Pop that up if you know. Quizlet, thank you. I've not heard of Anki, but Quizlet, Anki, but Quizlet's the one that my student used for anatomy and physiology. If you make Quizlet flashcards, share them. Put them in teams for other people to use. But yes, create Quizlet for the first 4 rows of the periodic table. Now, for sodium, I'm going to keep it. For chlorine, I'm going to replace the INE with IDE. So that's going to become chloride. And that is the name of NaCl when we write it that way. Now, when we have a compound where I can have multiple charges, such as iron. So iron exists as iron 2. It also exists as iron 3 plus as a cation. Now, anions, we don't tend to worry about this with anions, surprisingly. Common one for an anion is oxygen. That's O2 minus. Oh, yeah. So, if I have iron 2 plus with oxygen, it's that. If I have iron 3 plus with oxygen, it's that. Good way to get the formula is Fe2 plus, O2 minus, take this 2 down here, take that 2 down there. So that gives me Fe2O2, and then reduce it to the lowest possible integer. So if I divide both of these by 2, I get FeO. Here, they already are at the lowest possible integer. Now, the names do not reflect the subscripts here. And that's because this is an ionic compound and the subscripts are there to balance the charge of the cation and anion so that the overall compound is neutrally charged. So, but I do still have to, because I have 2 different irons, I have to identify to the person looking at the name which cation of iron I have for my compound. So, if it's the 2 plus, IUPAC nomenclature says this is iron 2 and then oxygen oxide. The older nomenclature said this is ferrous oxide. Both of those names are okay to use. We got away from ferrous because it didn't really give you the charge directly. And so you had to do a lot more memorization because the OUS meant +2 for iron, but it means +1 for copper. It means +1 for gold. So it carried different meanings. 2 always means +2. So that's why IUPAC went to this form of nomenclature. So this is the IUPAC standard. And today, this would be called a more common name. Iron 3 would be that's the IUPAC standard. And the more common name is ferric oxide. I will always use the IUPAC standard. So I'm not going to expect you to know common names. That being said, for some of these transition metal cations, it is still very common to use the common names, even though the IUPAC standard, this nomenclature changed 15 years ago as the standard. It's still pretty common to use the IUPAC names. Okay, that ends our second Pomodoro. No, iron will never be a 6+. I know why you're asking that, but if you look at the, and it's a good question, so I'm going to answer that question while we're in Pomodoro break, because that is a good question. I'm actually going to write it here in the whiteboard so everybody knows what I'm answering. Can iron be 6+? Okay, so if I were to write the electron configuration of iron, IUPAC, if I were to write the electron configuration of iron using the periodic table, the valence would be written argon, so those are the core electrons. And then I would have 4s2 and 3d 1, 2, 3, 4, 5, 6. So that's the electron configuration of iron. Now, going back to electron configuration review, if full S2 can only hold 2 electrons and it's full, P can hold 6 electrons to be full, D can hold 10 electrons to be full. And these are called subshells. That's correct. And then the 4 and the 3, the N, which here is 3 and 4, are called shells. And generally speaking, most stable implies full shells. Next most stable, so I'm going to do this most stable to least stable. Partial full subshells. And then in terms of stability between these two, you have full subshells and half full subshells. Now, when you are removing electrons, you always remove electrons from the highest shell. That means the highest N value. So, that means for this particular system, if I want to move an electron, so I want to go from iron to Fe+. That means I'm going to take an electron away. Initially, that electron is going to be taken away from the 4s subshell. But it's going to restabilize. This is going to restabilize into because technically the 3d5 is higher in energy. But so you might be saying, well, then why do we remove an electron from the 4s? It's bigger orbital, so it's easier to get the electron out of the 4s because it's out farther away from the positive nucleus. So it's easier for something to come and grab it, but that's not the most stable energetic configuration. So an electron from the 3D is going to fall down into the 4s. And that's actually that has a name. It's called shakedown. And you can see it if you're measuring fast enough, because that rearrangement happens really, really quickly. And that's part of the reason why an Fe plus can be a stable system, if you can get this shakedown. But it's not as stable as if I do Fe2 plus, that's 2 electrons out, I'm going to get argon 4s0, 3d6, which I can either write as argon 3d6 or as argon 4s1, 3d5. Again, these are two partial fields, and these two configurations, which one of these is technically correct? It's probably this argon 4s1, 3d5. And then if I do iron 3, removing 3 electrons, I get flat out argon 3d5. And it's that means that for ions, this is the most stable. Because I automatically go to a configuration that's got a half-filled suborbital and only has one half-filled suborbital. So the argon is all filled levels, and then I have a half-filled suborbital. So if I were to do 6 plus, and I could keep doing this, I could keep stepping down the electrons. If I were to do 6 plus, that would be argon 4s0, 3d2. And I'd have to, generally speaking, you don't move 2 electrons, you can only move 1. So the most of rearrangement I could get is an argon 4s1, 3d1, and that's not very stable. Now, the other reason why it's not uber stable is, generally speaking, it gets harder and harder to remove an electron as the charge goes up. Just because you get more and more positive charge, and the larger charge, the more attractive negative charges are to it, so it becomes harder to remove that next negative charge. There are a very few +4 cations. They tend to be in the 6 and 7 periods, i.e. the places where you also have that D block, that F block, so you have a lot more electrons and it's bigger. The one I know, well, I say that, but I think vanadium does a +4. I know tungsten does, and gold does a +3, and I think a +4. So there are possibles, but when you are stabilizing, doing this type of move an electron for stabilization to get half-filled orbitals, you can only move 1. 2 electrons are not going to fall down. Generally speaking, yes, that's a good rule of thumb. For electronegative, for radius, you don't have to worry about radius for the most part. Uh, Cations are smaller in radius than their neutral. Anions are larger in radius than their neutral. That's so that you should know. Uh, but we don't. You should have in your idea as you move down the periodic table as your uh, proton number gets larger. Yes, your atom gets bigger. Electronegativity is different. Points toward F. The most electronegative element on the periodic table is fluorine. And while fluorine can form covalent bonds, fluorinated compounds are weird. They behave differently than non-fluorinated compounds, and that's because that fluorine they react differently. They're very strange in organic chemistry. They have very strange properties in general in terms of their physical properties. And that's because that fluorine pulls is so electron negative, it really reduces the electron density from other things. Now, it is a halogen, so it can really only accept one covalent bond because it only needs one electron, but it's going to take the electron that it needs. So fluorine is the most electronegative. Now, the other thing that, and this is something we will cover, the other thing that we play with in this regard is the as the atom gets bigger, the intermolecular interactions get stronger. Those intermolecular interactions are called van der Waals forces. So the larger the atom gets, the stronger the van der Waals forces get. And those van der Waals forces can be stronger in terms of interaction of molecules with each other than the something like polar. So you do need to be aware of size. So size moves towards xenon. Electronegativity moves towards fluorine in terms of pointing arrows. So that means, like, if I'm comparing oxygen with sulfur, oxygen is going to be more electronegative than sulfur. But just slightly. And so that's how to view that. It is significantly harder to remove core electrons than valence electrons. And that's why core electrons don't ever form covalent bonds. So you're not going to share core electrons. You will share valence electrons, but not core electrons. Yeah, I have D holds 10. P holds 6. But there's only 6 for iron. And so half filled is 5. Well, the largest atom technically is oganesson, OG18. But it's not stable. It's radioactive. Generally speaking, francium and radium are things you guys are not going to play with. Xenon and radon as a noble gas is also radioactive. So technically speaking, xenon is a very stable, it's a noble gas, it's stable, it's not going to, the nuclei is not going to fall apart, it's not radioactive. So from a point of view of something you're actually going to handle in a lab, you actually will handle xenon in a lab sometimes. So I usually tell students, focus as the largest atom is it moves towards xenon. But yeah, that means that technically the one at 118 is the largest, because it's the very lower right hand of the periodic table. But if you're just needing to draw arrows to tell you size, just point it towards xenon and you've got it. So down and to the right. Other questions? Um, Karish, if you're curious about, as a spectroscopist, the way we kind of determine how hard is it to move electrons is what type of electromagnetic energy does it take for me to move them. So valence electrons can be moved around with visible and UV light. Core electrons take X-rays. So if I want to take an electron and move it somewhere, and it's a core electron, I'm going to have to put X-ray level energy into it to get that electron out. So, and that's why, at room temperature, you're just not going to form a bond with that. Filled ones are always more stable. Absolutely. So if you can get a filled subshell, that's best. But but if you don't have enough electrons to get a filled subshell, which we don't have in iron. Iron only has 26 electrons. I can't fill the D subshell with iron. So if I'm only going to put in enough electrons if I'm playing with cations, we're still on naming. I'm just answering questions about cations. If we're only going to do we can only play with what we've got. Now, can I make an iron 4 minus? That would give me a full 3D subshell, Fe4 minus. And that would be somewhat stable. And that's part of the reason why iron can conduct electricity. You can put electrons in, and those electrons will flow. But in terms of compounds, it tends to form ionic compounds. It tends to form a cation, not an anion. And the reason for that is it's got a lot of electrons, so it doesn't have a problem giving up some to share. And it's got fairly low electronegativity for that reason. Now, the other thing you need to know is electronegativity is a flat-out made-up number. It was made up by, I think, Pauli, but I'd have to check that. Pauli. And it was made up to explain ionic and covalent bonding. And he made up numbers that would work out and match certain experimental data and certain behaviors. There's no experimental way to measure electronegativity because it is a made-up scale. Okay? It works great, but it's one of those made-up scales. Now, we are going to swap over to Pomodoro 2, Pomodoro 3, and get back to naming. There are certain S can't be an S3. S can only hold 2 electrons. So there are certain molecular cations and anions. Now, what molecular, yes, P3 would be stable, more stable than, say, P2 or P4. Molecular cations and anions. These are things that would exist in an ionic compound, but are molecules, covalently bonded collections of atoms, not ionic interactions. There aren't that many cations. There is ammonia, ammonium. Do not confuse this with ammonia. Okay? Be very careful with those two names. There's peroxide. And there is, oh no, that's an anion. Sorry. I'm talking about cations. That is not a cation. The only two real molecular cations are ammonia and mercury 1. Those are covalent molecules that exist as cations. That you should know. And those are really the only two molecular cations that are in ionic compounds. In terms of anions, there are a ton of them, especially once we start adding like carboxylic acids. So which ones do you need to memorize? These two cations you definitely need to memorize. Which of the molecular anions, names and charges do you need to memorize? If they aren't on this list, I will not expect you to know them on an exam. And I'm always going to start by writing the most stable one first. That's nitrate. The less stable one is nitrite. On the 8, no. I mean, that's a good question. Hydronium, does it count as a molecular cation? That's a very good question, Dylan. We'll talk about that at the next break. So keep that question. I'm going to pin that question up at the top where I don't forget it. Okay, that's a really, really interesting question. Hydronium, it only exists in water. Technically, it is a molecular cation. The issue is it really only exists in water. If you have an acid releasing an H plus in ethanol or methanol or any other solvent, it's just going to release H plus. It's not going to form H3O plus. That doesn't inherently not make it an acid. It's just it doesn't hydrogen bond to water to form hydronium. So usually as chemists, I know like Dr. Altman makes a big deal about hydronium ions. Generally speaking, as chemists, we just write H plus. And when you get to organic chemistry, because almost no organic reaction happens in water, you're not going to write H3O plus. You're going to write H plus when a proton is moving around or has been given up by an acid. So hydronium is an ion. It does exist in water, but it's also not something you use that much in naming. So it's just not one of those things. It's useful to know, but it's just not really one of those things that we worry about in terms of memorizing. And I was trying to focus on what do I want you to memorize. So that one is just not one that I usually put on my list of should be memorized. Hydroxide's different though, because hydroxide actually will exist in organic solvents and is an important thing in an organic solvent. Okay. Sulfate SO4 2 minus. Make sure when you memorize this, you memorize the charge. Sulfite. Notice that the ite is always one less oxygen than the 8. Carbonate. That one, there is no carbonite. Has to do with Lewis structures. That might actually be a good homework question. I might ask that as a homework question. Phosphate. Now, phosphite is very, very unstable. These are the dominant ones of the stability. The 8s are always the one with the are the most stable. I mean, nomenclature is a made-up set of a codified set of rules that is determined by IUPAC, and they go over them about every 10 years and make changes when they feel they need to. So they just haven't changed this or come up with any other way to name these that makes any sense. So I'm trying to decide if there's any others I want you to know. That's why I'm sitting here thinking. Now, the other pattern has to do with the halogens. You can ignore fluorine. Like I said, fluorine's weird. Generally speaking, when we talk about halogens and forming bonds, especially bonds with oxygens or halo oxides, these are going to be formed with chlorine, bromine, and iodine. There is a reason for this. Fluorine is an N equals 2 period compound. That means it has no d orbitals in its ground state. N equals 2 does not have the possibility of a d orbital. You have to go to N equals 3 to get d orbitals. Now, the compounds in the period 3 row, like aluminum, silicon, phosphorus, sulfur, those, the 3d orbitals exist. They just don't have enough electrons to shove into those orbitals. But those orbitals are there, and that's why I can have SO4 2 minus. I can take some of those electrons that the oxygen can share, and I can shove them into the d orbitals, and I can form hybrid orbitals that incorporate the d orbitals in order to create a compound that can hold the number of electrons that are in a sulfate. Fluorine can't do that. Chlorine, bromine, iodine can, because that's an N equals 3, N equals 4, N equals 5. So definitely have d orbitals at the N equals 5. But fluorine doesn't have that. So there is no ability for fluorine to form anything but one bond. And that's because anything in period 2 at most can form 4 bonds. Cannot form anything more than 4 bonds, because any atom in row 2 of the periodic table at most can have 8 electrons around it in terms of its valence. And I'm going to only have 2 core electrons. So 4 bonds is 8 shared electrons. That's all it can deal with. So don't ever draw more electrons around any of the elements on row 2. Don't ever draw more than 8 electrons, be it bonds or lone pairs or just electrons in general. 8 is all they can hold. Don't put 5 bonds around carbon or nitrogen or boron. Don't put 10 electrons around nitrogen because you're trying to make a Lewis structure work. Nitrogen cannot accept 10 electrons unless you put it in an excited state spectroscopically. Now, if I shine light on it, I can get it up into an N equals 3 or higher orbital, and then I can put more electrons in, but it's not stable. When we're talking about chemistry, we're talking about things that happen in a stable state, that are happening at room temperature. No, phosphorus can hold, silicon can hold more than an octet. Any of the atoms in period 3 can hold an octet. Doesn't necessarily can hold more than an octet. It doesn't necessarily mean that they will, but they can. So there's a difference between will and can. Technically speaking, the things in period 2, the octet rule is an absolute. You cannot violate it in the ground state. Anything in period 3, you can violate the octet rule. Now, will it violate it or won't it? That's a different matter. And that has to do with stability and molecule size and a whole bunch of other stuff, and we just haven't found something that violates it in terms, in the world. But that doesn't mean it can't exist. For the second period, it cannot exist. You cannot violate the octet rule at ground state energies. In period 3, you can. For anything in period 3. It doesn't mean it will, but you can. Okay? That's a good question. So on the halo oxides, because they have a lot of electrons, they can do a whole bunch of stuff. So, the most stable of the oxides, fluorine always follows. It's not almost always. It always follows the octet rule. It's in row 2. So there is no almost on fluorine. Okay, so chlorine. The most stable of the chlorines is ClO3-, and that is called chlorate. If I add 1 oxygen to that, that is per chlorate. If I take 1 oxygen away from it, just like up here, if I take 1 oxygen away from phosphate, I get phosphite. If I take 1 oxygen away from chlorate, I get chlorite. But I can take 1 oxygen away from chlorite, and that is hypochlorite. Now, as we move around on this, the most reactive are at the far ends. Of these. And you really need to be aware of which of the direction. Hypochlorite is bleach. Sodium hypochlorite. When you buy Clorox bleach, that's what it is. Sodium hypochlorite. Perchlorate, so NaClO, bleach. Ammonium perchlorate, is rocket fuel. You need to be really aware of that. You do not want to inadvertently buy perchlorate or perbromate or periodate, because all of the bromine and I can replace chlorine with bromine and with iodine and get the same series. You do not want to buy the pers. They're very, very reactive, and because they're so reactive, we actually have to monitor them, test them every 3 months. It's a pain in the butt to have a per anything in terms of the halo oxides. Now, there is another per that you guys are aware of and you guys have used in chemistry, and that's permanganate. Manganate's another one of those that kind of forms this type of series. So permanganate is MnO4 2 minus. So there is a manganate, MnO3 2 minus. Ironically, I've never even used MnO3 2 minus, and I don't know how stable it is. But that's another one where you have an oxygen series, where you have permanganate, manganate. I'm not sure if you have manganite. I'll have to look that up. But I suspect you do because you have a per. So that's another common one that you guys will use that's an ion you should memorize. The way I go about memorizing the halo oxides is I remember chlorates have 3 oxygens. And then I just remember I add a per if I add an oxygen, and then I go from 8 to ite by removing an oxygen, and then hypoite if I remove to 1 oxygen. So basically, the way I memorize this is hypoite 1 oxygen, ite 2 oxygens, 8 3 oxygens, per 8 4 oxygens. Now, that rule obviously only works for the halochlorides. I mean the halogenated oxides, and also for permanganate. Don't apply that rule for phosphate. Phosphate's PO4 3 minus. The us is for an acid. See, I haven't put this in water. I'm not talking about an aqueous solution yet. Okay? OUS is only used if you are in an acidic solution. Again, you got to be very careful. And it's only used if you're in an aqueous acidic solution. So, It's again a very good question. HCl gas. Its name is hydrogen chloride. HCl aqueous, technically that is H3O plus Cl minus. This is hydrochloric acid. And that's why it has different names. Hydrogen chloride is a covalent with significant ionic character gas phase molecule. I take that gas and bubble it in water. I do a chemical reaction and generate H3O plus or H plus and Cl minus. So this is if it's an aqueous. If I bubbled it in, say, ethanol or methanol, there I would generate H plus in methanol and Cl minus in methanol. And I would not name that hydrochloric acid. Not actually sure how I would name that. I would just probably, I might call it, I'd probably call it hydrogen chloride and methanol. So I'd have to really look up how they name this in methanol. So hydrochloric acid is reserved for when HCl is bubbled into water. So the hypo-us and the ick is, yes, if I have it in, is if it's an acid in water. So if I have HClO3 aqueous, that would be chloric acid. If I have HClO4 aqueous, that would be perchloric acid. Notice the ick. If I have HClO2 aqueous, that would be chlorous acid. And if I have HClO aqueous, that would be hypochlorous acid. But notice, that's always in aqueous. So you have to be very aware of phases, of where, when you are naming even ionic compounds, when you are naming them, you have to be very aware of what they're in. Are they as a solid? Are they in aqueous solution? So are they in non-aqueous solution? What are they? Because here you might just say that this is hydrogen or hydride, and no, hydride is negative. So hydrogen. So I might just say this in terms of naming is a hydrogen cation and chloride anion. In methanol as a name. Yes. And you should know your acid nomenclature, that what we just went through. But yes, you need to know and memorize these polyatomic ions. If they are not on this list, I will give you the name. So things like arsenate and arsenic and selenide and things like that, I will give you. And obviously the elements like oxide, that one's just take the element name. Nitride, that's take the element name, that's N3 minus. Carbide, those come from the elements, so I expect you to know those. Hydride, H minus. So, but those are elemental, they're not polyatomic. They're atomic. Okay, so we are on break again, and because we are on break, I'm going to go back to that question that was asked. Does hydronium count as a molecular cation? That was one. I don't think that was the actual question. No, the question, that was the wrong question. That's not the one. Unpin. The one that was asked that I said I would come back to is the mercury one. Hg2 2+. Why is this a molecular cation? Why? Now, do keep in mind mercury is weird anyway. But let's look at, again, let's go back to that electron configuration. If I look at mercury, I've got sorry, I needed to sneeze. I have 6s2. Sorry. I have xenon, so it's a big compound. 6s2, 4f14, 5d10. That is the electron configuration of mercury. And part of the reason why mercury is a liquid at room temperature, it's the only metal that's a liquid at room temperature, is because it's so big. Remember I said that the size of an atom determines how it interacts with other atoms and molecules? Mercury is huge, so it strongly interacts with itself, and that's why it's a liquid at room temperature. The stronger the interactions, the more likely you're not going to be in the gas phase or in the solid phase. Why it's not a solid, I have no idea. Don't ask me that one. Because all of the other ones around it are solids. So why it's a liquid and not a solid, I don't know. That one I can't answer. Now, when I take an electron from this compound to form 1, I get xenon 6s1, 4f14, 5d10. And that's a half-filled orbital, but with two really big filled orbitals. When I take 2 electrons from it, I get xenon 4f14, 5d10. So this is very stable. All full suborbitals. Very nice, very stable. This one, I've got this half-filled suborbital, but it's really a big half-filled suborbital. That electron is way away in terms of space from the nuclei that's got a, plus 80 charge. Because that nuclei inside Mercury is plus 80. So that electron, it's a long ways away, and there are a whole bunch of electrons between that 6s electron and that plus 80 nucleus. So, and Mercury is very big, it's strongly interacting. So because of that, if I really wanted to stabilize this, it would be very handy if I formed a covalent bond and I shared that 1s electron. Because if I do that, I get an Hg plus, bond it to another Hg plus, and the electrons that they're sharing are 6s1 electrons to form that covalent bond. That's why you get it. You don't get that for Hg2 plus because there's no advantage to sharing electrons. The real more interesting question is, why doesn't cadmium do this? And the only thing we can figure in that regard is because cadmium doesn't have the F electrons. So this is one of those instances where those additional 14 electrons between the valence and the nuclei matter in terms of the ability to form bonding. Now, another one that does behave strangely is gold, and for much the same reason. Gold forms a fairly stable covalent molecule with chlorine. And it's acidic. It's an acidic compound. And that is, in fact, one way you can dissolve gold, is to put chlorine in it, and it'll dissolve. So the elements in period 6, they don't necessarily always behave the same as the other metals in period 4 and 5. And that is because of that influence of that full F block. So, I mean, we use gold, we use platinum. Platinum's a great catalyst. We use iridium, also really good catalyst. So gold, platinum, iridium, all really good catalysts. Mercury, we would probably use it as a catalyst, but when we try to use it with organic molecules, it becomes really, really toxic, really, really fast. I mean, it's pretty toxic as a metal, but organomercuries are extremely deadly. So we tend not to use it. But the elements in period 6, the metals in period 6, they have really different properties than the metals above them. They don't play quite the same as you would expect. But good question, really good question. The reason for that is size, and the reason for that size is that F block. But extremely good question. Yep, that's exactly it. Hg2 2+ is more stable than two separate Hg plus ions. Now, how did we determine that? How do we determine that for any of these? We're going to talk about that this semester. The way we know is that when we have an ionic solid, and we want to know what happens when is this a molecule or is it an ionic salt? We have a solid. We don't have any clue about it. We want to know, is it an ionic salt or is it a covalent molecule? We try to dissolve it in water. And then we measure its freezing point depression or its boiling point elevation, because that tells us how the boiling point of the aqueous solution changes, tells us how many ions we have in solution. And that tells us the stability of what we have. So we know when we take mercury chloride and mercury 1 chloride and we dissolve it, we get chlorine 2 and we get 1 for we get 3 ions. And we not 2. That's how we know that the mercury had to form a 2+. And we also later, when we developed X-ray spectroscopy and the ability to look at crystals spectroscopically, we could see that it was a mercury 2, chlorine 2 crystalline structure. But initially it was because of how it changed the boiling point of an aqueous solution, or the freezing point. And we will cover that this semester, so you'll see that. But again, good questions. So, for review on the rest of this type of nomenclature, inorganic nomenclature, I will put the reading from the OpenStax textbook on nomenclature in the review module. But at this stage, for our final go, we're going to start at 9:50. I'll quit. And it'll be a 30-minute. We're going to talk about covalent nomenclature, but specifically carbon covalent nomenclature, i.e. organic nomenclature. And carbon, it can form so many different types of bonds, and so many different things can attach to it, that there's this entire, the nomenclature of organic chemistry is so complex that it's in a book, and for the most part, not even organic chemists can name the compounds that they make. So there's software that we have where you draw the compound in the software, and then you select it with a lasso, and you tell the software, name it. And the software names it for you, following the rules, IUPAC rules for naming that compound. And that becomes its name. And those names are usually so long and so complicated that in organic chemistry literature, it's only ever named once. And it's also given a number. And then for the rest of the paper, it's just referred to as compound number 50. It's not referred to by name. It's just referred to as whatever number it was given in the figure where you drew it in a research paper. Now, if it turns out that compound's important and other people want it, and the company picks it up and purchases it, and then it's going to make it industrially, then it's going to be given a common name or a short name or an abbreviation, so that they do not have to write the full name on the label. So, for instance, I use a lot of laser dyes. They have names like rhodamine 545. That is not the IUPAC name. Rhodamine refers to a particular molecular structure. It's got certain things hanging off of that particular scaffold that makes it a rhodamine. Those things hanging off adjust the wavelength at where it lasers to 545. That's the maximum lasing power, is at 545 nanometers. And that's how it's named, and that's how it's labeled. Because the IUPAC name would be so long that you'd have to, because you don't, these compounds are expensive, so you buy like 1 gram, so it's a really tiny bottle. Your label would stick out past the bottle. It wouldn't, the name wouldn't fit on a small bottle label. It is an issue because by law, all compounds must have a name, and they must be named. You can't just write the formula on the label. So a lot of times, compounds that you're storing, if you're in a research lab, they'll be stored by compound number, and that number will be, it'll be like notebook 1 compound 50. So then you go find your lab notebook 1 and you look up compound 50, because you don't have a name for it, or the name's so long it's you're not going to put it on a label. So most of what in the other 114 classes, they do not teach organic nomenclature. I teach organic nomenclature because it makes it easier for us to talk about compounds during the semester, 1. 2, it introduces you to it before you hit organic chemistry, and that makes the first, up to the first exam of organic chemistry, a lot easier. So it gives you kind of a head start on your organic chemistry 1 class. So the students who have had me for 114 and come back after Orgo 1 really appreciate having been introduced to organic nomenclature. And I actually introduce it in 113. So like my 113 students, when we cover nomenclature, we will cover it in 113. I reintroduce it in 114. And then when you get to organic chemistry, you have some confidence in organic nomenclature. Okay. So, the first thing you have to do, just like the first thing you have to do for inorganic nomenclature, is determine the, is it ionic or covalent? The first thing you have to do in organic nomenclature is determine the functional groups. Because the functional group, organic nomenclature, let me answer, somebody popped up a question. Yeah, it'll all be found in an OpenStax chapter. It's 113 stuff. You guys were taught this in Gen Chem 1. That's why I just reviewed it quickly, and I'm not going to go over it anymore. The organic nomenclature you were not taught in Gen Chem 1 unless you had me, and I know you didn't, at least not last semester. So I'm going to cover it now. I just wanted to make sure. Give me just a minute real quick. I want to give you the order of functional groups. Now, at this stage when we cover organic chemistry, I'm actually not going to expect you to know how to name complex functional groups in organic chemistry. So there's only a specific level of nomenclature I am going to expect you to know. But I am going to expect you to be able to recognize functional groups. So you don't have to come up with the name, but you do have to be able to recognize that this is this type of compound, this is this type of compound, and so forth. So it's more about naming the functional group, not So being able to recognize and go, okay, this is this type of functional group. Oh, you're right. Class ends at 10. Thank you. I thought 10:20. My brain did a freak. We will pick this up next class period. But I'm going to go ahead and post the functional group image that I grabbed in this one, just so you have it. Okay? No, that is not what I wanted. Give me just a minute. Sometimes software does not play the way I want it to. Apparently pasting is not an easy thing to do here. Try this one more time. And now I should be able to insert images. Oh, did it again. Sorry, sometimes I have to get stuff set up and I forget that I need to set it up a particular way for pasting into non-standard documents. There we go. So this is the table. This is the image that we will start with next lecture. But in terms of naming, the only one that I will require you to know how to name are the alkanes. So that. Alcohols. And haloalkanes. And we will do a little bit of discussing of naming arenes. But the rest of this we will be leaving for and a little bit of amines, not a huge amount. But the rest of this table we are leaving for organic to teach you how to name. But you do need to be able to recognize the pattern of functional groups. So you need to be able to, for instance, tell the difference between an amide and an amine, or an amide and an imine. So those you do need to be able to recognize the difference between and be able to distinguish. So the functional group, but not how to name it based on that functional group. So the only ones we'll learn how to name are alkanes, alcohols, haloalkanes, and a little bit of arenes and amines, but not a lot. Okay? So, thank you for catching that. For reminding me that class ends at 10. So, I shall talk to you guys later. If there are no more questions, I will end this stream. And thank you for being here. Yes, the readings are going to be posted. But again, if you have trouble reading the OpenStax textbook, don't hesitate to get you a different textbook. Okay? I'm not sure why you added the calendar tab to the top of the hybrid chat. It's in the team. So the shared calendar is in the actual team. So I'm removing it from the chat. Please go and look at the calendar in the actual team, not in this chat.